Thank you for joining this series from PGL Solutions. In this video, we will talk about what is the design process and why is the system broken. This video is part of a series of blogs on systems engineering and the design process published on our main site. A link to our site can be found in the description of this video. In the previous vlog, we talked about the design process. At first, to the untrained ears, the whole thing just sounds like technical jargon, a punchline about something that's very useful. What untrained ears, you may ask? You may fall in this category if you haven't worked in industry for at least a couple of years and haven't been involved in a full product or project cycle. Or if you were not one of the very few that selected a technical major in college that actually included a course called design, referring to the process, not aesthetic design, and you actually took it. But what is it really? Is it the design of how a product will look or feel aesthetically? Probably not, since we also attached the word process to it. Or is it then the process that one follows when creating a product? And what process is that? Well, if you did take the class or know it from professional experience, then yes, some would describe it as a set of steps recommended by industry based on knowledge derived from many years, more like decades, of product development and likely polished by academia later on. With input from these different sources, the process itself likely went through multiple iterations and refinements to eventually reach a mature shape that, if understood and followed thoroughly, increases the developer's or team's chances of creating a high-quality product. What follows next is merely a synopsis of what the design process actually is in an attempt to demystify some of the terms used in the context of product development and maybe serve as an incentive for you, engineer, maker, DIYer, or tech entrepreneur, to dig deeper into the subject. From a technical point of view, a design process starts by determining what the system or product needs to do and inquiring into why. Some of the key questions for defining requirements are: is it relevant to the customer? If so, in what way is it needed? Does it satisfy a basic need, or is it more of an excitement specification? Is it necessary? Is it clear and concise? Is it feasible? Is it traceable? Can it be tested? For reference, you can also check out our previous video dedicated to the what and requirements definition in the description below. Once the requirements are defined, you will need to think about how you will implement those requirements, and once again ask yourself, why that way? Take, for example, one of the most typical dishes from the south of the United States, shrimp and grits. Grits are made from ground corn, typically crushed or chopped corn, which is later cooked in milk or water. How can these two main ingredients, combined and cooked with other ingredients, result in a dish that has the same name and yet many very different presentations and tastes? Well, that has to do with how the ingredients are combined, the order of the different steps, and how it all gets cooked. And that is what design and implementation are all about. There are indeed different ways of solving the same problem. Here, you and the team will make full use of all the tools and technical knowledge you have learned empirically, from books, from instructors, etc., to achieve your own implementation that must ultimately fulfill the agreed requirements. And then what, you may ask? Well, there is probably a team of people working alongside you, right? Most of the times, yes. The stakeholders. Are they knowledgeable? Well, if they are there working with you on a product or project, it's likely because of their merits. So yes, you and the team need to leverage each other's knowledge. In an interview with the Dutch tech giant ASML, one of the interviewers told me a phrase that I hope never to forget. 1 + 1 is not 2, but 3. One of the most powerful tools that classroom lectures fail to teach is the power of alignment and communication within the team. In an ideal world, communication between teammates is easy, constant, and quick. In reality, though, some, maybe most, work environments see a different reality. To tackle some of the communication barriers, one can resort to review sessions, in person, through email, or both. This essentially accounts for a content owner who presents the information to an audience or sends it out for the audience to review and give feedback on. This is easier said than done, as it involves personal accountability and project accountability, namely a common commitment to success. From your own competency, based on your technical knowledge, what contributions can you bring to the table? Is there something wrong, something requiring a correction? This is one way in which teams can think together and be self-critics. In 1930, world-renowned French painter Francis Picabia released one of his most famous paintings, named Elo. I hope this is the correct pronunciation. If not, feel free to leave a comment with the correction. Do your best and be nice. The painting became the centerpiece of MoMA's 2016 exhibition, and it was titled, "Our Heads Are Round, So Our Thoughts Can Change Direction." How is this applicable to engineering design, you may ask? Well, if the common thinking of the team is lazy, not proactive, not self-critic, it will likely never change direction, even when it should. Maybe it won't even evolve at all. There is also technical management accountability. The project lead or tech manager in charge of the project should verify that a significant amount of reviewers have provided input to the content owner, maybe not 100%, but at least the key stakeholders, before signing off and moving forward to the next phase. From part level to system level testing. A portable electronic product will likely be divided into an electrical subsystem and a physical module. Among other things, the electrical subsystem will be characterized by a PCB design and the electrical components, the code used to program the control unit, if there is one, its physical size and dimensions, thermal response, and of course, it will depend on a manufacturing process to make it a reality. The functionality of the PCB, including for instance code logic or machine states, input to output response, may be governed by a transfer function, electric connections to the peripherals, I/O, etc., must be verified first before integration with the casing takes place. In parallel, the casing that holds the electronics will itself be the result of a CAD design, material and color selection, probably in accordance with outgas and thermal specifications, and a manufacturing step. Just as with the electronics, the final properties of the casing, dimensions, special material properties, color tones, etc., will need to be evaluated against the corresponding specifications before integrating the casing with the rest of the product. Once the independent pieces are known to satisfy their independent requirements, the integration of the components takes place, resulting in an initial prototype. The integration phase can be as simple as physically mounting and attaching components together. However, in many cases, interface points are the most vulnerable ones due to a multitude of reasons that are beyond the scope of this video. Finally, once put together, the high-level system specifications are validated. This means we are no longer talking about component-level evaluations, such as scoping electrical signals in the PCB or assessing rigidity of the casing, but we evaluate the product functionality as a whole and against end customer expectations. These expectations are in fact an interpretation made by the developers, say for example engineers or makers, about what the end customer really wants. In larger companies, this is commonly done by technical marketing teams. In the end, such end customer needs drive or simply become the so-called high-level requirements, which should be agreed on and documented at the beginning of the project, following requirement definition best practices. And so, there is a process. When talking about a process, what we are doing is defining a set of actions and organizing them in a specific manner that from start to finish yields repeatable results. This is a highly desirable feature in the context of product development. Now, if the process is as good as advertised, why would we keep it theoretical? Is this another dangerous case of book learning? Okay, that's the starting point of many of the things we know, and granted most, probably all, ABET-accredited engineering programs in the United States have a capstone design class that is mandatory during a student's senior year. But is that enough? One could argue that it should in fact be applied, not just thought, in as many team projects as possible in technical schools, colleges, etc. Unfortunately, this is typically not the case. While startups are known for their fast pace of innovation and ability to change course rapidly, such way of operation comes at a cost. For example, lack of structure, which usually impacts quality and robustness of mass-manufactured products. By exposing technical students early to the design process as a collaboration and structural tool, they will have a smaller learning curve when joining a dynamic team, and the team itself will benefit from a higher yield sooner. Technical minds can focus on implementation without putting too much effort into fitting in and contributing within the collaborative environment. The design process becomes second nature sooner. An analogy can be made with sports. The faster we can get all team players, junior and senior, to understand the strategy and modus operandi of the team, aka way of work, the more chances we have of making it to the playoffs and ultimately winning the entire tournament. Meaning, maintain or increase a technical edge over the competition, develop faster, lead the industry, increase profits, etc. And if understood and experienced sooner through multiple iterations, it should also be easier to improve on it, develop it, trim its fat, and still evolve quickly. And that's it for this video. Thank you for joining us. Don't forget to visit our site for more content and training on systems engineering.